Welcome, everybody. My name is Gautam Kunapuli, and I'm the author of Ensemble Methods for Machine Learning. And today I would like to talk about gradient boosting from scratch, which is chapter 5 in this book, which is currently in MEEP. Here are some links if you want access to these slides. They're on my GitHub page. The link to the book, as well as the companion Jupyter notebooks with the book, are all over here as well. So let me give everybody a few seconds here to pull these up if you need them. So, gradient boosting. It's all over the place these days and is widely considered the state of the art in machine learning. If you've ever taken part in a Kaggle competition or are generally interested in seeing what all the Kagglers are doing these days, and also if you've been reading a lot of machine learning blogs and things like that, you'd have probably seen the term gradient boosting pop up a lot. And it's being used for a wide variety of data science problems and challenges. And so it is rightly considered one of the state-of-the-art machine learning algorithms. So we're going to kick off here by motivating, the need for gradient boosting and why we need to understand it by posing this highly bothersome yet utterly unavoidable question: which machine learning algorithm should I use for this data set that I have? Right. And this is, of course, an age-old problem. Everybody wants to know the answer to this question. And, over the last few years, last couple of decades even, there have been extensive studies by various authors in academic circles, at least, to try and figure out what the answer to this is, right? And so um, this first work in 2014, for instance, analyzed about 17 families of machine learning algorithms on 179 data sets, right, which are publicly available. And they concluded, based on the algorithms and models that were available at that time, that random forests were the best, and their performance was comparable to support vector machines. And this kind of represents, uh, you know, um, our understanding of the state of the art at that time, right? So the 90s and early 2000s were all about support vector machines, and then we transitioned to random forests, which are also an ensemble learning method. And now, more recently in 2018, a study was performed, and in this case, they also threw in gradient boosting classifiers, right? And what they came up with was that out of the 165 data sets, that compared them pairwise, and here are the algorithms and the families of algorithms that they compared, right? So we have gradient tree boosting, random forests, extra random forests. These are all Ada boost is in here. These are all examples of ensemble methods. But also, some classical machine learning algorithms such as, stochastic gradient descent, k-nearest neighbors, decision trees, logistic regression, and so on and so forth. And, the leftmost column is basically the percentage of data sets that these algorithms were able to beat gradient boosting on. So for instance, random forest was only able to beat gradient boosting 9% of the time on these 165 data sets, right? So if you were to go ahead and rank all of these algorithms, you'll see that gradient boosting, and these are all results from this paper by Olson et al., right? That gradient boosting is in fact the most successful on a wide variety of data sets that they considered in their study. And up there are several other, ensemble methods such as random forests and extra trees and AdaBoost, somewhat fallen behind. And so this kind of gives us, a way to answer this highly bothersome yet utterly unavoidable question: which machine learning algorithm should I use for my data set? And all of this, seems to suggest that gradient boosting is where we want to go. And this kind of sets up our motivation for looking at gradient boosting today, right? And so gradient boosting is a sequential ensemble method. Um, in short, it's an ensemble method, which is essentially a collection of machine learning algorithms, right? So you put together, instead of training one giant model, you train several models, and then you put them all together, uh, and you aggregate their predictions, and that essentially gives you a machine learning ensemble. And commonly, there are two types of machine learning ensembles. One of them is known as parallel ensembles, where several models are trained in parallel and their predictions are aggregated together to give a final prediction. And in typical cases of parallel ensembles, the base models, which make up the ensemble, are typically strong learners. And a strong learner is one where you would expect, good performance, high performance, basically as a rule of thumb, right? Sequential ensembles, on the other hand, operate sequentially, as the name suggests. So what they do is they take the data that you have and build a first model, and then they try to identify where that model is failing. Essentially, so in terms of a classification problem, it would mean you'd want to try and figure out where the first model that you trained, M1 over here, is failing, and then you try to train a second model, M2, such that the predictions on those misclassified examples are improved upon, and then you see how well the ensemble of M1 and M2 is doing, and then you try and identify now what the misclassifications are, and you train a third model to add into your ensemble, and so on sequentially, one after the other, right? So this is in direct contrast to the parallel ensembles where all of these models are kind of trained together in parallel, whereas in sequential ensembles, you have to train them one by one because the one you're training currently will have to fix the mistakes of all the models that you've trained so far, the ensemble that you have until now, right? So gradient boosting is an example of a sequential ensemble algorithm. Parallel ensembles, I'm sure you're familiar with. They include methods such as bagging and random forests, um, whereas sequential ensembles include methods such as boost, which is adaptive boosting, and what we're going to look at today, which is gradient boosting, right? So the key for sequential ensembles that we want to keep in mind is that every time they train a model, they do so to basically fix the mistakes that have been made by the previous model. And the other thing you want to keep in mind when it comes to these kinds of sequential ensembles, such as gradient boosting and eta boost, is that the base estimators, these models that you're training in every iteration, are typically weak learners. So a weak learner, in contrast to a strong learner, is basically a machine learning model that is not overly complex, that achieves, you know, reasonable performance. In absolute, in strict terms, a, a, a weak learner for classification has to do barely better than random guessing, right? And so it turns out that you can put together a whole lot of such weak learners to boost their performance into a strong learner. So that is basically what sequential ensemble methods do, and that is exactly what gradient boosting does as well. Uh, and so, since we're talking about gradient boosting, it is also, ideal to delve into this and try and figure out how they achieve this key thing, which is to identify the mistakes that have been made by the current model, right? And to do so, it's also kind of useful to characterize what gradient boosting does, and then contrast it with what other boosting algorithms such as eta boost do, right? So for these sequential boosting algorithms, the key is to identify where the mistakes are and get the base learning algorithm to focus on these misclassified examples. So in the case of eta boost, the figure on the left, you can see that this is a binary classification problem over here and a simple illustration, and you can see that there are two misclassified examples. There are the squares and the circles, but there is one of each that is misclassified and on the wrong side of the classifier. In order to get the base learning algorithm to focus on these in the next iteration, AdaBoost uses weights. So it has a clever way of computing weights, and so the more confident it is that it has done the correct classification, the lower the weight will be. basically saying that I think I have classified these data points correctly, and so they will have lower weights. On the other hand, if they're misclassified, then those corresponding points will have higher weights, which here are these 2 points, the circle over here and the square over here, which are misclassified, and so they would have higher weights. And in this way, you give these training examples along with their weights to a base learning algorithm, and you can use that to train a weak classifier. On the other hand, gradient boosting also needs a way to, characterize the misclassifications of basically characterize the mistakes made by the algorithm, figure out what's going on, and in a similar way to AdaBoost, get it to focus on those specific data points. But instead of using weights, it uses something called residuals. A residual is just an error, right? So in this case, again, with these 2 training examples, if AdaBoost gives them high weights, gradient boosting will essentially compute residuals, and the sign of the residual, as well as its magnitude, basically give us an idea of which way we should push our new model to adjust its behavior so that it does correct classification. So this is kind of the intuitive basis for the difference between AdaBoost and gradient boosting, right? And this is essentially going to be the core focus of what we're going to be looking at over the next 30 minutes or so, which is essentially how can we measure these residuals for these training examples, which ones essentially do we focus on when we build our models, how all this works in practice, what do the trained models look like, and so on and so forth. So the other thing that gradient boosting does is it approximates gradient descent. Now, gradient descent is an example of an optimization algorithm. Basically, anytime you have a loss function in any machine learning problem, you ultimately want to optimize your loss function. And many machine learning algorithms use several different types of optimization algorithms, one of which is gradient descent. If you're familiar with neural networks, there's a variation of gradient descent that neural networks use called stochastic gradient descent, and there's a whole lot of variations on that front, and so on and so forth, right? But broadly, you can think of gradient boosting in general, but specifically gradient boosting as a means of approximating gradient descent. So in this case, for instance, in the example on the left, you have this loss function that you want to optimize. It's a squared loss, right? So a loss function essentially is going to tell you how badly you're doing or how well you're doing, right? So here, the squared loss is going to measure the difference between the true label, which is y, and your predicted label, which is f0, for this particular model. And then it's going to square the difference. So if the difference between the true and predicted is pretty big, the square is going to be bigger still, and the loss is going to be a large number. On the other hand, if y, your true label is close to your predicted label, then what's going to happen is that their difference is going to be small, which means that the squared loss is also going to be correspondingly small. So this is a way for, a loss function is basically a way for us to characterize for each training example, and indeed over the entire data set, how well the model that we have at the moment is behaving, right? How is it performing? And you can obviously, measure your loss on the training set. And the goal, of course, is to keep updating your model until you achieve small loss, right? That is what training is in the overall grand scheme of things. And so when you use an approach like gradient descent, an optimization method like gradient descent to do training, then it's going to also essentially iteratively compute a sequence of steps. And it's going to basically move from your current solution to the next solution, and then update it again to the next iterate, and then update it again to the next iterate until we converge, right? So at the bottom here, you can see This is just an example function, right? What happens with gradient descent, right? This could be an example of a loss function, very similar to the squared loss. It's got two minima over here, and so how does gradient descent work? You begin with some initial guess, and then you compute the gradient. The gradient basically is the slope at that point, right? But interestingly enough, the negative gradient is going to tell you which direction you should be going in so as to get the biggest decrease in your loss function. So in this case, the negative gradient, if it's going to look in this direction, you move in that direction, and then you get to your next iterate, which is your function f1, and then you're going to compute the gradient there, move in the opposite direction to the gradient, and continue to descend. That's going to get you to f2, and then you're going to carry on to the next iterate, to f3, so on and so forth until you converge. This is how gradient descent works. It's a classical optimization algorithm. On the other hand, gradient boosting is going to work in pretty much a similar way, right? But instead of explicitly computing the gradients at each iteration, we're going to learn to approximate the gradient at each iteration. So what this lets us do is you can see that, here, if you replace the true gradient with this thing that we've learned, the final model that we have, F3, is really going to be, if you backtrack from here, right? F3 is going to be, this, this H3, which is your approximation here, plus H2, which is your approximation here, plus H1, which is your approximation here. So sequentially, what you will do is you'll start with your initial guess. You will then build a weak learner here to perform, this approximate gradient descent, and then you will end up at a model which is essentially F0 plus this weak model. And now from here, you compute the gradient again, and then you learn a weak learner, a weak estimator. And now your new model is going to be F0 plus H1 plus H2, right? So you've sequentially added a weak learner to it. And now you're going to repeat it. And when you get to F3, your F3 is going to be F0 plus this weak learner, plus this weak learner, plus this weak learner. So F0 plus H1 plus H2 plus H3 until you get to, and then you keep carrying on with this procedure until you basically terminate in this case. And you have and there are some criteria for termination that we can talk about later. So this is essentially the analogy between gradient descent, which is commonly used in optimization, over loss functions, and here gradient boosting, which is basically a procedure that also tries to capture this kind of behavior, right? And so putting all of these things together, gradient boosting can be viewed as gradient descent, which is an optimization algorithm, and boosting, which is an ensemble method. So if you, and that is precisely what gradient boosting does, right? So remember, to recap, what boosting wants to do is it wants to sequentially learn these weak models, one model at a time, in such a way that we are fixing the mistakes made by the previous model. And what gradient descent does is it sequentially updates your your progress over this loss function profile. And so you can see now through these two that your gradient descent um, and boosting combined together essentially gives you a gradient boosting procedure. So the key then is that we are going to be, instead of explicitly computing these gradients, we are going to be training weak learners, because that is what boosting does, to essentially capture and the mistakes that the current estimate makes, and then go ahead and fix them by using the residuals as a means of understanding how far off we are and how much we need to adjust our current model. And so here's, what gradient boosting would look like. The very bit of simple pseudocode, really, right? And so, much like gradient descent, we're going to start off with an initial guess. And the initial guess over here, typically we just pick it to be 0 or some constant value 1, whatever. So, this is our loss function profile that we're interested in minimizing. And so we start off at some initial guess. So, and what do we do now? We make our predictions, right? So our predictions over here are all going to be F0 because that is our current model. Our current model is a constant, irrespective of what your input is going to be, whatever training example you give it, it's always going to return a prediction of F0. This is our first iteration, right? And so everything is our predicted values at this point over here at our first guess are all going to be F0. And we already know what our true labels are going to be, so we can compute the loss. But the loss itself is not immediately helpful, because while it tells us how badly we're doing, it doesn't tell us how we can fix the model, right? Basically, the idea is the loss you can think of as just a magnitude, whereas the gradient of the loss is going to give you a residual that is going to be either a positive number or a negative number, right? So, and that is going to tell you for one particular training example how much you have to fix the model, either in one direction or on the other, right? So that is basically the idea over here, is instead of using weights to characterize misclassifications, we're going to use these residuals to characterize misclassifications. So that's really, so after you initialize, what you do is you compute these residuals for every training example at this point over here. So what you end up with is this little data set that you've constructed, right? So the loss, which measures the error, the residual, which tells you how much we are off by. And the key thing to remember is that the residual we compute is actually the negative gradient, because the residual tells you how much we are off by in which direction. So if we want to fix our model, we'll have to go in the opposite direction for that training example, right? And so you do this for every single training example. You try and figure out how much they're off by and what you need to do to fix it. And so for every training example, essentially you compute the residual and you create a surrogate data set. The surrogate data set that you have over here is the training examples, as always, but instead of using, the training examples xi over here, but instead of using the labels, the true labels yi, as we would normally do in a classification procedure, we use the residuals instead, right? So we construct this surrogate data set. And so what this is going to allow us to do is it's going to allow us to compute an approximation to the gradient. Actually, it's going to allow us to learn an approximation to the gradient at F0, which is where we are currently, right? And so this can be used now to fit a weak learner over our training examples. So we fit a weak learner with the training examples are features as usual, but instead of the true labels, we use the residuals. Essentially, what we would end up doing then is we would end up fitting a weak learner that approximates the true gradient. So what is a weak learner? In the context of machine learning, a weak learner is just a simple machine learning model. So in gradient boosting, as in a lot of boosting methods and in general ensemble methods, but boosting methods especially, uh, decision trees are commonly used as weak learners. So uh, what kind of setting would you have to do to ensure that the decision trees you're learning are weak? It's the depth of the tree, right? So a decision tree that is very, very deep is going to be much more complex, which is going to allow it to fit all the data points as much as possible. And so its fit is going to be great, but it also may tend to overfit. And it is also going to be correspondingly more complex, which would make a very, very deep tree an example of a strong learner. On the other hand, if I fit a shallow tree, a stump, for instance, of depth 1, or something of like depth 2 or 3, just very, very shallow trees, then what I would end up with would be a weak learner, right? Because it is not going to be as complex as a strong learner, but it is quicker to train, and it, in a sense, really captures and approximates, in this case, the gradient, right? So it doesn't have to get everything right. It just has to get some things right. And that is not a problem for us if we're missing a few things, because in the next iteration, we will have an opportunity to train yet another weak learner to fix the mistakes of whatever we were not able to capture in this iteration, and so on and so forth, right? So and so by collecting a bunch of these weak learners, we're going to build a very strong learner. But so here, after computing the residuals, we fit a weak learner to the residuals, and these in most modern gradient boosting implementations are typically decision trees. Um, and you, of course, have the ability to control the depth of those trees, and it is ideal to fit a weak learner, hence a shallower tree, right? The one final thing that everybody should keep in mind when it comes to gradient boosting is that the residuals that you compute for a loss function that you have is going to be a real value, right? It's going to be a real valued number. It's going to be a continuous value, which means that this surrogate data set that you've constructed over here has a training example and this label, which is a residual, a continuous value, which means that if you want to fit a weak learner on this surrogate data set, you're going to have to do it using a regression algorithm, which means that the internal uh, model that gradient boosting algorithms use are always going to be regression algorithms. This may sound a little confusing or counterintuitive at the start because you can say, hey, I'm really interested in a classification problem, but you're telling me that I have to fit a regression problem inside? And the answer is yes. So it doesn't really matter what the overall loss function you're going to fit is, because gradient boosting is really interested in capturing misclassifications or basically discrepancies in classification problems and regression problems or ranking problems as a measure of these residuals. And because the residuals are continuous values, the weak learner and the base learning algorithm inside gradient boosting is always going to be a regression problem. So this is kind of the overall framework of gradient boosting. There's one last thing that some people may gloss over typically, but it's an important point worth making. Essentially, if you're drawing parallels between gradient descent and gradient boosting, right? In gradient descent, once you've computed a descent direction, it is often the case that you also attempt to compute a step length, because descent direction really tells you which way you need to go, but it doesn't really tell you how far you need to go. So, so in this example over here to the left, if I start off at F0 and only went this far, I would end up over here. On the other hand, if I went this far, I would end up over here, and so on and so forth. Right? So the choice of the step length is very, very important. And gradient descent does this using line search, which is a simple optimization procedure in its own right. What We can do this in gradient boosting as well. In fact, the earliest, um, you know, academic papers that proposed gradient boosting tended to exactly use a line search. And even now, if you look at the pseudocodes in a lot of places, they will also include the step that says compute step length. But from a machine learning standpoint, in addition to building a nice model quickly, we're also interested in doing it quickly, right? And so one of the things that is commonly done is, instead of explicitly computing a step length, it is also common. It is also common to essentially make this a constant term that is often referred to as a learning rate. And you may have heard this term learning rate before, right? So every time you compute a gradient, or in this case, every time we fit a weak learner, we're going to essentially um, apply a learning rate to it in the front over here when we update the model. What this essentially does is it limits the contribution of each of these weak learners to the overall model uh, based on what the value of the learning rate you've chosen is. So if your learning rate is very, very small, then we're going to need a lot of weak learners to basically build a strong boosted model. But on the other hand, if your learning rate is very large, then it is very likely that you will just keep on overshooting where you need to be going, and that may slow down your convergence in other ways as well, right? So typically, uh, in our implementations, when we're using gradient boosting in practice, it is a good idea to set the learning rate by a cross-validation procedure, or basically by using a validation set, by using good machine learning practices to ensure that we are making sure that we select this learning rate appropriately um, during training. So what I'm going to do here is really pull into one of the Jupyter notebooks that is associated with this chapter. Um, and we're going to look at an example of gradient boosting from scratch, right? So we're going to look at a classification problem. We're going to write out a loss function. We're going to, calculate its. If we're going to write out another function to compute these gradients, which are essentially the residuals, and then we're going to essentially build our gradient descent procedure, and then see step by step what it's actually going to be doing over here, right? The code for this, this Jupyter notebook itself, is on my GitHub, which is along with a whole lot of other companion notebooks, for the book. So uh, let's just run through it, right, and see what's really going to happen over here. So here's a very simple data set, make moons, which we're all quite familiar with, I'm sure, right? So we're going to use scikit and NumPy broadly. And so the data set that we have, make moons, is basically, we're going to visualize it over here in a second, right? So let's just go ahead and do that. So this is essentially a simple two-dimensional data set, right? So I've created a data set of 200 points. It's a binary classification problem. There's some noise, so you can see that there's a bit of spread over here between the positive and negative examples. And as you can see, this is not a linearly separable data set because there is no linear classifier, straight line classifier essentially that can fit this, right? So that is just not possible. What we need then is a nonlinear classifier. The question is, can we get gradient boosting to build us one, right? So we're going to use this very simple two-dimensional example to visualize how gradient descent basically works step by step, right? So for classification so what we have here is a classification problem. So what we will need now to do classification is a loss function, is a means for us. If I have trained a model, say F, how well is that model doing right now? I need a way to characterize for every training example, as well as for the model as a whole, how well we're doing, right? And so there's a lot of loss functions for classification that exist out there. Um, there is the cross entropy, which is essentially a logistic loss, right? That is commonly used these days in deep learning and neural networks. There are things like exponential loss, and there's the hinge loss, which is commonly used in support vector machines. And also, over here, we're going to be using the squared loss, which is often used in regression problems. But here, under specific settings, actually it works out quite nicely for classification problems as well sometimes, right? So we're going to use the squared loss, and we're using the squared loss mostly because it is easy to differentiate and compute its gradient and implement it. And so that's why we choose this particular example over here, right? So what does the squared loss look like? It's basically going to be, so yi is the true label, f is your model, and xi is your training example. And so what is the squared loss? Plug your xi right into error f, you're going to get a prediction, and then take the difference between the true label and the predicted label, and then of course you square it, right? That's just your straightforward squared loss over here. So the gradient for the squared loss, you can also compute with respect to your f. And if you remember your gradients, from calculus, then that's what we've done over here, right? For one single example, the loss essentially, as if the squared loss is going to be y minus f squared, and so the gradient is going to be minus y minus f, right? Uh, and of course, this is what we're going to use to characterize how well we're doing overall, right? So this is actually very straightforward to implement, these residual computations, right? So let's come down here. So we are interested in learning with these residuals, right? So before delving into the implementation, let us go back to the slides over here and look at the steps that we have, right? So we initialize and then we compute. So for in every iteration, we compute these residuals, and then essentially we have to fit a weak learner. And this weak learner is a decision tree regressor in our case now. But that is what we're going to be implementing. It's going to be a decision tree regressor. And then there's also going to be a step length over here, right? So this is kind of written up over here as well, right? So as before, we'll put our intuition into practice, and this is exactly what's going on. So now, how do we translate this pseudocode to the code we have over here? So we create a function called fit gradient boosting, and it is going to take in the training data, the training labels, and in this case, another parameter, n estimators, which is essentially going to tell you how many weak learners you have to train. This is essentially how many iterations you want your gradient boosting to run for before terminating, right? So the ensemble that you get is going to be one weak learner or one weak estimator per iteration. And so it's going to run, in this case, for 10 iterations, and it's going to give you an ensemble of 10 models that you can use for prediction, right? And so what we do is we create an empty list of estimators, and as we learn in every iteration an estimator, we're going to put it into this structure over here, and then F, as you can see, this is our initialization, right? So in this case, if you may recall, the initialization step, it just says initialize the ensemble overall, like our prediction, initialize it to some constant value, and so we initialize it to 0. What this means is that in my first iteration, what is my prediction going to be? It's just going to be 0 for everything. It doesn't matter which training example you get, the output's just going to be 0, right? So in this case, it's going to predict 0 for all of these positive examples, negative examples. In our first iteration, it's going to be 0 all the way through, which of course is not particularly helpful. And so that is where the magic of the algorithm, we're going to see that here in a second, right? So now we're going to learn in sequence, because this is a sequential algorithm, one estimator at a time, right? So we have these residuals that we're going to compute. So our residuals, as we have before, are going to be the negative of the gradient. And since the gradient was minus y minus f, the negatives get canceled, so it's just y minus f, right? So the negative residuals, the negative gradients are your residuals. So this is the true labels for all the examples, and these are your predictions for all the examples, and the residuals are just going to be the differences between them, right? For the squared loss function. It's obviously going to be different for other loss functions. You'll have to, so if you want to use cross entropy loss, then you'll have to replace the residual calculation with the gradient, the negative gradient of the cross entropy loss, or any other loss function that you want to use, right? And so here, once we have the residuals, our next step is to fit a weak decision tree, right? A regressor to this surrogate data set that we've constructed of your data points as well as their corresponding residuals. And to do that, we will use scikit-learn, scikit-learn's decision tree regressor package, because it's very easy to use, very easy to have in there. And because we're interested in learning, basically building weak estimators, we are going to set max depth equals 1. Typically, so that's going to give us a decision stump for regression. We can set it to 2 or 3, something shallow basically, right, for the simple problem that we have in mind. And then we build our very first weak learner for the first iteration over here. And then, and now we want to, now that we've computed our weak learner, we want to put it into the ensemble, but we also in this implementation explicitly compute the step length rather than use a learning rate, and that is done with the help of this function known as minimize scalar. So minimize scalar is a function that that we get from SciPy, and it's a built-in function that basically allows us to do this exact line search. So this so these 3 steps over here essentially implement this line search procedure, which essentially tells you how far you want to go. That helps us compute this alpha over here, and then we update our ensemble predictions. So our F over here, the model that we've learned, is going to be our line search times this this new regressor, this weak learner that we've learned, and we append them all. So let's look at this in practice. There's another function. So this giant bit of code over here is essentially the same thing, but it's got a whole lot of visualization stuff wrapped in it so that we can look at it iteration by iteration, right? So let's run this and let's see what happens, right? So remember, so we're going to go over this iteration by iteration so you can see what exactly it is doing, right? So this is a classification problem. It's a binary classification problem. It has 2 classes, right? Which are essentially the squares, which have a label y equals +1, and the circles, which have labels y equals -1. So that is first thing we want to keep in mind is the labels, the true labels are +1 and -1 for the 2 classes respectively. When we first begin, remember that we initialized our model to just give 0 as our answer, right? So the answer is just as our prediction. The predicted label is 0 for every training example. So what is the residual? For positive examples, it's going to be true minus predicted, right? For positive examples, it's going to be true minus predicted, right? Which is going to be 1 minus 0, right? Because our prediction is going to be 0 for everything. The true for positive, for squares is going to be 1. For circles, the y is going to be -1. That's the true. And the prediction is still going to be 0. So the residuals essentially are going to be 1s for one class and -1s for the other class, which is exactly what we have over here. So we compute the residuals explicitly based on our current initialization, which is 0. What are our residuals? For the squares, they're all 1. And for the circle, the other class, they're all -1. And so once we've explicitly computed our residuals, our next step is to fit a decision stump, a regression model to these, right? And so here on the right, you can see the regression model that we have essentially fit to it. And it's going to be this nice step function that we have over here. This is a decision tree, right? This is the decision tree regression algorithm. And you can see that it kind of fits a lot of things right? Over here, but it's already missing some of these examples. Why is it missing some of them? Because it is a weak learner. It is not a strong learner. Its purpose is not to go ahead and fit everything that it possibly can, right? We want to quickly fit as much as we can, as effectively as we can. And that's why we have trained a weak learner over here, right? So this is essentially what it's doing. And now if we flatten this, look at it from the top, the model that we've actually learned looks a bit like this, right? Now you can see that what is it doing, right? It's doing pretty well. In our first iteration, just starting with predictions of everything being 0, we actually managed to train a model that has 16% error, right? That's not bad at all, right? So what it's doing is it's predicting this big clump of circle data points correctly. It's predicting this clump of square data points correctly, but there are a significant number of mistakes still, right? 16% of the data, which our data set, remember, is 200 data points. So that's quite a few, right? That's 32 training examples are misclassified, and you can see that there's a few circle red ones over here, and there's a bunch of squares over here that are misclassified. Over here on the right, it looks exactly as the one on the left, because what we're doing is we're plotting each individual weak learner as well as the entire model, the entire ensemble prediction that we have. Since we've only done one iteration, we've only inserted one weak learner, so they both look exactly the same as they should, right? So now, when we move on to the next step, we would like to go ahead and train a second weak learner such that it addresses and fixes the mistakes of the first one. So now we're going to have to compute residuals with respect to this ensemble that we have, which currently contains only one example, right? And so these are the residuals we end up computing. Now, intuitively, if you look at this, just forget the residuals for a second, right? If you look at the figure over here on the right, and you say, which data points do I want to focus on? If you were doing this manually, which ones do you think you want to work on, right? You would say, I would like to make sure that the next model that I train, the next weak learner that I put into my ensemble, essentially fixes this clump over here and this clump over here, maybe also these few examples over here that are misclassified. Basically, the idea then is that the residuals that we're computing should be able to, assign. They should be higher for these misclassified. They should be notably higher, not as close to 0, right? For these misclassified examples. And so when we compute our residuals as we head into the second iteration, we can see exactly that, right? Is that these few training examples over here essentially correspond to these points, and they have very high residuals corresponding because they're misclassified, right? And then we have this clump over here, which are over here, and they also have high residuals, and similarly, these misclassified points that we have over here have high residuals, but with negative signs on them, right? So the magnitude of the misclassified points when it comes to their corresponding residuals is the highest for these. And what this is going to do when we build our next model is it's going to force the weak learner to try and fit those training examples that have the biggest residuals in magnitude, right? And that is a good thing because in that way, we will be able to get it to look at the examples that were not correctly classified in the previous iteration. So what we want to see is some kind of weak learner that either correctly classifies these examples or these couple of small red circles over here or these red circles over here. And in fact, given the residuals that we have at the moment, the weak learner that we train in the second iteration is going to fit and correctly classify, these examples over here. And now you can see that it has actually pretty high error with respect to everything else. You know why? Because we told it to forget about all of these other data points and focus only on the ones with the high residuals, and that's exactly what it did. So the weak learner that we have over here did what we wanted to do with respect to the residuals. So by itself, again, it is not that great. But now remember that our ensemble already has a weak learner that we have from our first iteration. So we put this one in there as well. And now the two together, as you can see, we have this plus this, and now you get this, nice little L shape over here. And now the overall classification error, training error, over here has dropped from 16%. Now that you've increased your ensemble by one more, it's dropped to 9%, right? And we carry on. So in iteration 3, now we have this entire ensemble. Now look at this ensemble and ask yourself, which ones are currently being misclassified? And the answer is this over here, right? This clump over here, and we still have our two favorite little groups that were left over from before. And so in the next iteration, we will compute the residuals, and we hope that the residuals are going to be highest for the ones that are misclassified. And that, in fact, turns out to be the case. Now, you can see that for every data point, the residuals are now beginning to separate, right? You have these really badly misclassified ones over here. You have some misclassified ones over here, so on and so forth, right? So there's a clear stratification in the residuals. And the weak learner over here, it's still pretty weak, so it wasn't able to get all the way up to the top, but it was able to fit. And this is the weak learner that we get. And the overall ensemble looks like this, right? So as we go through all of these ensembles, you will see now in every iteration, as we go through the iterations, you will see that it starts adding these weak learners one by one. So in iteration 3, it adds this weak learner, but remember that along with line search, the overall model doesn't seem to change that much. In iteration 4, it adds a slightly different weak learner. The overall model looks the same. And then iteration 5, it's adding this. And in iteration 6, it's adding that. And so let's actually rerun this for all of them, right? Let's make this 6, 7, 8, 9. Just so we can explicitly see what all of these weak learners turn out to be, right? So in iteration 1, this is our first weak learner. This is our overall model. Iteration 2, overall model. And now you can see what each of these are looking like. Just keep an eye on the overall model, right? Like at some point, it is going to you're going to add enough weak learners to now start changing the profile of your ensemble, and ultimately, by the time you get to 10, you're able to the error over here drops from 9%. But down to 8% in iteration 8, and then by iteration 10, you get 2.5. You can get different behaviors by changing the learning rate. You can force it to move faster, slower. You can increase the contribution. So here, there's an implementation of a line search, but in fact, it is possible to replace the line search and put in a constant learning rate. And what you're going to end up with is essentially, you can control the behavior of and the contribution of each individual weak learner in the ensemble. So this is essentially what gradient boosting does, is it looks at the residuals and it trains at every iteration these weak learners, so that as we keep adding more and more weak learners to our ensemble, the overall ensemble's performance is now boosted into a strong learner. So that is essentially visually what a great way to see what gradient boosting actually works like under the hood, right? Um, so let's jump back over here now, right? So we've looked at how gradient boosting works. So this is the implementation that comes with the book, and of course, gradient boosting quite popular, which means that there's a whole lot of other resources that are also available for this. And here's one that I like a lot, that I have played with in the past. And this is a fantastic resource to kind of play around and visualize, what gradient boosting really does as you do a lot of different things, right? So let's go over here. Um, it's an interactive playground. It's a really cool resource, um, and so you can change several things about your this gradient boosting implementation, right? So you can change the depth of the trees, and as you do so, you can see that the learners, as the overall ensemble that you have over here, as well as the individual, models that we were also looking at, and that's what you have over here. You can see, right? Remember that the tree depth essentially controls the complexity of the model that we have, right? Of each of these weak learners. So trees that are depth one, essentially stumps, or two, or something like that. The shallow trees basically are not at all complex, and they're very weak. And trees that are very deep are very complex, um, and strong, right? So you can see here what these individual weak learners look like, in that as you increase the depth of the tree, each of them becomes more and more complex and stronger in its own right. Um, and you can play around with that. And then, of course, let's just set this to 2, for instance. And then you can also look at the learning rate. The learning rate, again, we talked about this a little earlier, but this is again a great opportunity to see what it does, right? So a slow learning rate really causes it to converse it slower. An over high learning rate will cause it to potentially overfit. And so these are like various considerations you can have. And of course, one last thing you can keep in mind is the difference, between the training loss and the test loss, right? So there's a lot of parameters that you get to play with when you build your own gradient boosting algorithm, right? We're obviously not going to use our own implementations. There's a lot of powerful off-the-shelf packages, which we're going to talk about here in a second. But these are very nice implementations that exist. But generally, to understand how you should select some of these parameters for your models, this would be a great place to play around, right? So if you basically make a model that has very very deep trees and set a very very aggressive learning rate, you can see that you get a very very nice model when it comes to your training loss, right? It achieves nearly 0% classification error here, but its test loss is about 24%. And that is not good. In fact, that is an example of overfitting, is that you've done such a great job on your training set, but you're doing so poorly on your test set. It means that the model you've trained has overfit to your training set and is not going to, do well when you deploy it. It's not going to predict future examples well at all, right? And that is a consequence of, building over complex models, over complex uh, over complex models and over complex components of your decision tree, of your ensemble. So that's a cool resource. You should go and play with it. It's a lot of fun, and really gives you a great understanding of what to do, right? So and yeah, so that's basically what's going on under the hood for gradient boosting, right? And to immediately jump into gradient boosting, the easiest way to do it, of course, is to use scikit-learn's implementation of gradient boosting, um, which does not offer as much flexibility when it comes to all the kinds of loss functions you might want to put in there. But it is definitely quite viable, very helpful, especially as a learning resource, right? But for more practical applications, if you do a search, you'll see that there are a lot of tools that are available out there for gradient boosting. Um, there's LightGBM, which we're going to talk about here. There's XGBoost, which you've undoubtedly heard of, which we'll talk about on the next slide. And there are several others. H2O AI has their own implementation of gradient boosting. There is Cat Boost, which is a gradient boosting that is specifically tailored for categorical problems. So there's a bunch of different implementations, and broadly they offer very similar kinds of performances, the similar kinds of functionalities, but under the hood, they're all doing, things in a slightly different way. And we're going to talk about a couple of those things here. So, like GBM, for instance, which is a publicly available open source gradient boosting framework, was developed and released by Microsoft. It's been out there for a few years now. This is covered in Chapter 5 in the book, basically the ins and outs, how it's used, so on and so forth, right? How does this differ from the gradient boosting we were just talking about? Well, it is essentially, it scales up much better. And one of the ways it scales up much better is by improving the underlying training algorithm itself, right? So the weak learning algorithm underneath that we have, the base learning algorithm, is essentially a decision tree regression algorithm. And remember that when you're doing decision tree regression, you'll have to figure out what a good split point is for your tree, right? And it turns out that this is one of the most time consuming and computationally expensive parts of decision tree regression is you'll have to consider all possible unique values of a feature to figure out where you're going to split. So if I have a data set of, I don't know, 100,000 data points, that means I have to consider. So an example here is if I have a 1D regression problem with 50 points, what is a good split? Well, I can put a split between this point and the other 49. I can put a split between this point and the other 40. That's exactly what is shown over here, right? Is I can put one split between every gap, uh, in every gap between two training examples, right? And I have to consider all of these and evaluate all of them to figure out which one is the best split, which can become very, very time consuming if you use classical decision tree regression, um, learning type, splitting procedures. So what Light GBM fundamentally does, and there's a whole lot of other stuff they have going on in there as well, but fundamentally they implement a histogram-based splitting approach, right? Which is instead of like considering all these exhaustive combinations of splits, they are going to bin the data first and only consider the splits between the bins, right? Which, depending on how well you bin, is going to give you the ability to greatly reduce the number of um, splits that you have to consider, which in turn greatly accelerates your learning. Right. Another reason Light GBM is a great tool to play around with and use is because it supports a large number of loss functions for classification problems, regression problems, ranking, so also things like multi-class classification, ordinal regression, stuff like that. But most importantly, you can also create and use your own application specific custom loss functions, right? So this is something that a lot of people do on Kaggle, for instance. Is there's a lot of application specific work where people spend a considerable amount of time understanding the data, understanding the domain, and then trying to build loss functions that are tailored to those particular domains. And this is where tools like LightGBM and XGBoost, which also has that functionality, come into play. And of course, support for parallel and GPU learning is also there, right? So this is LightGBM, a very, very useful tool. And then in the same vein, another powerful gradient boosting framework is XGBoost, or Extreme Gradient Boosting, which is covered in Chapter 6 of this book, which is currently under development. But the key difference between light GBM, which really at the end of the day implements a slightly more sophisticated version of what we talked about earlier, um, right? So that's what light GBM does. XGBoost, on the other hand, takes it further and implements a different, a slightly, a more advanced version of boosting called Newton boosting, right? So gradient boosting, as the name suggests, uses gradient, which is first order derivative information, right? So it uses derivatives, whereas Newton boosting uses first derivatives as well as second derivatives. And this is actually, so using this extra information helps you build better models, right? They also has other ways of regularization, and regularization is basically some way to control overfitting, right? And so it at a high level, it really is quite effective because it offers additional mechanisms to control overfitting, which means that if you're able to select your parameters properly through validation set, cross validation, whatever, you will be able to build downstream models that are going to generalize pretty well, actually, right? So and as with LightGBM, XGBoost also supports a large number of loss functions for classification and regression and ranking. And as with LightGBM, you can also create and use application-specific, data sets. And also, of course, support for scalable computing and big data is also a core feature of XGBoost. And that basically concludes our discussion on really gradient boosting from scratch, where the idea was to put together, a gradient boosting algorithm ourselves, absolutely from scratch, so that we could really take it apart from under the hood and understand what's going on in there, so that when we go out there and use all of these tools like LightGBM and XGBoost, we're not mystified by why they behave as they are, right? Because now we know what learning rate can potentially do for us as we change it. Now we know, what the effect of uh, making your trees deeper is going to be, and now we know how to do all of these things that can go into essentially building uh, nice and robust models for the tasks that you have at hand. So thank you all very much. I will be here for a few more minutes. If you have any questions, please post them in chat and I will answer them. Thank you.